Welcome. In this video, we are going to talk about integration by partial fractions. Let's begin this lecture with a motivational example. Suppose that we were asked to evaluate the integral x plus 5 over x squared plus x minus 2. Notice that x plus 5 over x squared plus x minus 2 can be rewritten as 2 over x minus 1 minus 1 over x plus 2. This integral is quite easy to evaluate. It's simply 2 times the log of x minus 1 minus the log of x plus 2 plus our constant. So, as you can see, the challenge is not evaluating the integral, it's converting it from this original fraction to this expanded set of two fractions. And to do that, this is where partial fractions will come into play. So partial fractions we will be utilizing for a rational expression in the form of a numerator over the denominator are both polynomial coefficients. And there's multiple cases, so let's go over each one, and then we'll do plenty of examples. So in the first case, if the degree of the polynomial in the numerator is larger than the degree of the polynomial in the denominator, we will want to go ahead and use polynomial long division to simplify the rational expression. Next, suppose that the denominator is a product of distinct linear factors. So this is the case that we had in our initial example. Notice that x squared plus x minus 2 can be rewritten as x minus 1 times x plus 2 simply by factoring. So when we have, let's say, k distinct linear factors, we will rewrite the initial fraction r over q as a1 over a1x plus b1 plus a2 over a2x plus b2, and so on all the way to ak over akx plus bk. And once we've written it out in this form, we would go ahead and use systems of linear equations to solve for a1, a2, all the way down to ak. Now our next case, suppose that the denominator contains repeated linear factors. So let's say it was like x minus 2 squared as the denominator. Then let's say that it is x minus 2 to the rth power. Then we would go ahead and use r over q equals a1 over a1x plus b1, and so forth all the way to ar over a1x plus b1 raised to the r power. And we would solve for a1, a2, all the way down to ar. So this exercises all of our cases in which we have linear factors. So now what we need to do is we need to introduce when the denominator contains irreducible, non-repeated quadratic factors. I'm not going to have a generic formula for this one. I'm going to go ahead and give you an example. So suppose that we have the expression x over x minus 2 times x squared plus 1 times x squared minus 4. We would go ahead and write this, well, we have the distinct linear factor x minus 2, so a over x minus 2. Then we have two quadratic factors, so we would have bx plus c over x squared plus 1 plus dx plus e over x squared plus 4. So basically for a quadratic, the numerator will be a linear factor. And then our last case scenario will be the denominator containing irreducible and repeated quadratic factors. And in this case, we will go ahead and use the form a1x plus b1 over ax squared plus bx plus c plus, let's say, a2x plus b2 over ax squared plus bx plus c squared all the way down to arx plus br over ax squared plus bx plus c to the rth power. In that case, we would solve for a1, b1, a2, b2, and so forth to ar, br. All right, so I'm sure that that felt a little bit fast for you. I promise we will go over it very carefully as we do each example. But let's go ahead and start doing some problems. So let's start with the first example. Suppose that we are asked to evaluate the integral x cubed plus x over x minus 1. Notice that the degree of the polynomial in the numerator is 3. The degree of the polynomial in the denominator is 1. The numerator has a higher power than the denominator. Therefore, we are going to go ahead and perform long division. So we need to compute x cubed plus x divided by x minus 1. And we'll go ahead and write this in the following way. We'll write x cubed, and technically this is plus 0x squared, just to prevent any confusion. I'm going to write that 0x squared right there, plus x, and we're going to go ahead and divide this by x minus 1. So now let's go ahead and think. X goes into x cubed how many times? It goes in x squared times. And x squared times 1 is, well, negative 1 is negative x squared. And x squared times x is simply x cubed. Let's go ahead and subtract this expression, and we're going to get, well, the x cubed terms will cancel each other. Then we get x squared, and do not forget to bring down the x. And now we'll perform this. X goes into x squared how many times? Well, that's simply x. And then x minus 1 is negative x. And x times x is x squared. When we subtract, the x squared terms will cancel out, and then it will leave us with 2x. We'll go ahead and perform this division as well. So x goes into 2x, well, twice. And then negative 1 times 2, well, that's negative 2. And then 2 times x is 2x. And when we subtract this, we have a remainder of 2. Notice x goes into 2. That simply cannot be done. All right, so now that we've performed the long division, we'll go ahead and evaluate the integral. So this is going to be equal to, well, x squared plus x plus 2 plus 2 all over x minus 1. And our challenge now is going to be evaluating this integral. But actually, this is a really easy integral to evaluate. This is simply going to be equal to 1/3 x cubed plus 1/2 x squared plus 2x plus 2 times the log of x minus 1 plus our constant. And that will be our answer. All right, let's go ahead and do another example. In this example, suppose that we're asked to evaluate the integral of x minus 1 all over x squared plus 3x plus 2. All right, so the polynomial in the numerator is of lower degree than the power of the polynomial in our denominator. So we don't have to do polynomial long division. Notice that x squared plus 3x plus 2 can be easily factored into x plus 1 times x plus 2. Those are distinct and linear factors. So, x minus 1 all over x squared plus 3x plus 2. That can be written as a over x plus 1 plus b all over x plus 2. And it's going to be our job to solve for a and to solve for b. Now what we're going to do is we're going to add these by using common denominators. Well, we want to actually have the common numerator. So, because we're going to compare the coefficients of the numerator to this common numerator that we'll make. And I'll show you what I mean by that. I know that was a little confusing. So x minus 1 is going to be equal to a. Notice that the denominator of a already has x plus 1, but it does not have x plus 2. So a times x plus 2 plus b, which has the x plus 2, but it does not have the x plus 1. And now we're going to go ahead and write a linear system of two equations in order to solve for a and b. And we'll do this by comparing coefficients. So let's take a look at our x terms. We have ax and we have bx. So a plus b is going to be equal to, what's the coefficient of our x term? It's going to be equal to 1. And then let's take a look at our constant term. I'll call it the 1 term. Well, we have 2a and b, so 2a plus b is going to be equal to, well, the coefficient of our constant term is minus 1. And this is a very easy linear system to solve by substitution, and you will get that a equals negative 2 and b equals 3. And now we have done the side work that is necessary in order to evaluate this integral. So let's go ahead and bring this all the way down here. And we get that the initial integral is going to be equal to the integral of negative 2 over x plus 1 plus 3 over x plus 2. And as you can see, this is a very simple integral to evaluate, and it's just like the this type of integral is just like the one that was used in our motivational example right above here. So this is simply going to be equal to negative 2 times the log of x plus 1 plus 3 times the log of x plus 2, and do not forget your constant. And that will be our final answer. All right, let's go ahead and do once again another example. So suppose that we're now asked to evaluate the integral of 1 all over x plus 5 squared times x minus 1. So notice that there's a distinct linear factor, x minus 1, and then we have the repeated linear factor of x plus 5. So 1 over x plus 5 squared times x minus 1. This is going to be equal to a over x plus 5 plus b over x plus 5 squared plus c over x minus 1. And now we'll combine everything to make one numerator, which is equivalent to 1. So basically we have that 1 is equal to a. The a has the x plus 5, so we need an extra x plus 5 and the x minus 1. X plus 5, x minus 1. plus b, which is only missing the x minus 1 factor. And then we have plus c, which is just missing the x plus 5 squared. And to solve for a, b, and c, we'll go ahead and create our linear system. So let's begin with our coefficients of our x squared term. Well, we're going to have ax squared and cx squared. And notice that there is 0x squared for 1. So we're going to have a plus c, set that equal to 0. Now let's go ahead and do our coefficient for the x term. We are going to have, well, if we FOIL this out, we'll have 5x minus x, which is 4x. So it'll be 4a. Then we have plus b. And then we're going to have plus 10c. And since 1 does not contain an x, we'll go ahead and set that to 0. Now let's go ahead and go over our constant coefficient, which is the 1 term. We're going to have negative 5a, and we're going to have minus b, and then 5 squared is 25. And the constant term is simply equal to 1. So we'll set that equal to 1. This becomes a system with 3 equations and 3 unknowns. Go ahead and solve that for a, b, and c. You obtain that a is negative 1 over 36. B is going to be equal to negative 1/6. And c is equal to positive 1 over 36. So now we're going to go ahead and take, let me change colors here. We're going to take this integral, and we're going to use our partial fraction decomposition to write down our final solution. All right, so this is going to be equal to negative 1/36 over x plus 5 plus negative 1/6 over x plus 5 squared plus 1/36 all over x minus 1. And this is a simple enough integral to evaluate. So this is how it's going to look. So this is going to be equal to negative 1/36 times the log of x plus 5 plus 1/6 times 1 over x plus 5 plus 1/36 times the log of x minus 1. And do not forget your constant c at the end. And that is going to be your final answer. All right, let's keep rolling on these examples. This is great practice for everybody. So we have exhausted all of the cases in which we have linear factors. So let's go ahead and stir the pot and introduce a quadratic factor. And in this example, suppose that we're asked to evaluate the integral x squared minus x plus 6 all over x cubed plus 3x. So as you can see, the denominator can easily be factored into x times x squared plus 3. So we'll have a distinct linear factor, and we'll have a distinct quadratic factor. So what we're going to do, x squared minus x plus 6 all over x cubed plus 3x. We're going to go ahead and write this fraction in the form of a over x plus bx plus c all over x squared plus 3. And let's go ahead and combine everything together. So x squared minus x plus 6, that's equal to, well, a times x squared plus 3. Then we have the bx plus c, and well, after expanding, it comes out to plus bx squared plus cx. Because basically, the bx plus c term, that's just missing the x from over here. And now we'll go ahead and compare our coefficients. So let's start off with our x squared term. So we have ax squared, we have a bx squared. And we have our coefficient of x squared on the left is equal to 1. So we got a plus b, set that to 1. Now let's go ahead and compare our x coefficient. So the only thing that has a coefficient with x is c. And x coefficient on the left is equal to -1. That's easy enough. And let's go over our constant term. So we have 3a. That's the only one. So 3a is going to be equal to, well, the constant term on the left is equal to 6. This is a pretty easy system to solve itself. You get that a is equal to 2. You get that b is equal to -1, as well as c being equal to -1. Now that we've performed the partial fraction decomposition, we'll go ahead and proceed in actually evaluating the integral. So this is going to be equal to the integral of 2 over x plus -x minus 1 all over x squared plus 3. And what I'm going to do is the -x minus 1 over x squared plus 3, I'm going to go ahead and split it as the sum of -x over x squared plus 3, and then -1 minus 1 over x squared plus 3. And I'll just write that out. So it's going to be 2 over x minus x over x squared plus 3 minus 1 over x squared plus 3. So we're going to evaluate the integral of these 3 pieces here. So the 2 over x, that's a very simple one. That's just going to be 2 times the log of x. And then over here, for the second portion, if we let u be x squared plus 3, it's a simple u substitution problem. And then we would obtain -1/2 times the log of x squared plus 3. And then 1 over x squared plus 3, if you have your antiderivative formulas memorized, this is equal to -1 over root 3 times the inverse tangent, and I'm going to write it down here, times the inverse tangent of x over the square root of 3 plus our constant. So once again, we have 2 log x minus 1/2 times the log of x squared plus 3 minus 1 root 3 inverse tangent of x over root 3 plus our constant. And this is our final answer. All right, we are going to do one more final example, and then we will be finished for today. Suppose that we're asked to evaluate the integral of 1 over 1 plus the cubed root of x. And we're going to do a definite integral from 0 to 1. So the first thing that we notice is we can't actually use partial fractions for this because the denominator is not a polynomial. This is actually a lot simpler. This is going to come down to a u substitution. So let's go ahead and let u be equal to x to the 1/3, i.e. the cubed root of x. This will come useful later, but do be aware that x is equal to u cubed. All right, now we have that u of 0, well, 0 to the 1/3 is 0. And then u at 1, well, 1 to the 1/3 is also equal to 1. So then we have du, well, that's going to be equal to 1/3 times x to the negative 2/3 dx. And then by simple algebra, we can change this. So we'll call dx and set that equal to 3u squared du. So how we go from the second to the bottom line to the bottom line, so we move the 3 over, so we have 3 du equals x to the negative 2/3 dx. Then we would have, if we multiply everything to the other side, we would get how would we say this? We would get x to the 2/3. Yes, exactly. We would get x to the 2/3. No, my apologies. It would be x to the we would multiply both sides by x to the we would want it to be x to the 2/3. Yes, it would be x to the 2/3. Sorry for the confusion there. So we would multiply that. So we would have x to the 2/3, and then remembering that x is equal to u cubed, you would have, so x to the 2/3 is equal to u over 3 times 2 over 3, and that becomes 3u squared. There we go. That's our side work, so I'll set that aside here. So I'm going to set this integral equal to, well, our ranges of the integrand do not change, so we're going to have the integral of 0 to 1 of 3u squared all over 1 plus u du. Now notice that the power of the polynomial in the numerator is larger than the denominator, so we're actually going to have to do a polynomial long division again. So we're going to do 3u squared plus 0u plus 0, divide that by u plus 1. So u goes into 3u squared, 3u times, then we get 3u times 1 is 3u, and then we have 3u squared. Go ahead and subtract both sides, and we obtain negative 3u, and then don't forget to bring down that 0. And then we have u goes into negative 3u. Well, that's going to be negative 3 times. And then we're going to have 3 times 1 is negative 3, or negative 3 times 1, sorry. And then negative 3 times u is negative 3u. Subtracting that, we obtain 3. And u going into 3 cannot be done. So we've done all the work that we needed to do. So this is going to be equal to the integral. Go ahead and set that aside as well. So this is going to be equal to the integral from 0 to 1 of 3u minus 3 plus 3 over 1 plus u du. I do apologize if you can't read that, but it's 3u minus 3 plus 3 over 1 plus u du. This is a very simple integral to evaluate. This is going to be 3 halves u squared minus 3u plus 3 times the log of 1 plus u. And we're going to go ahead and evaluate this definite integral from 0 to 1. And the final result, after some simplification, you will receive 3 times the log of 2 minus 1/2. And that is your final answer. If you are uncomfortable with polynomial long division, I do highly recommend going onto YouTube and reviewing some videos on polynomial long divisions from your prior algebra courses. And this is how we integrate by partial fractions. Thank you, and we'll see you next time.